Some students find confusion between units newtons per kilogram and meters per second square for acceleration. Let's say a few words about these units. When we use the equation A equals delta V over delta T with units meters per second, that's meters per second, our units are meters per second square. That's meters per second for change in velocity, and units second again for the corresponding change in time. When we use Newton's second law for acceleration, A is F over m, our units are newtons per kilogram. That's so many newtons per so many kilograms. What goes on here? Is it meters per second squared, or is it newtons per kilogram? It turns out both are equivalent. Let's see why. Our unit of force is the newton, with 1 newton defined as the amount of force acting on a 1 kilogram mass that will produce an acceleration of 1 meter per second square. Dividing by kilogram, we can see that units newton per kilogram end up as meters per second square. We see the units are equivalent. Either can be used when expressing acceleration. A few words about the acceleration due to gravity and weight. Newton's second law, A equals F over m, can be also written F equals ma. When the net force on an object of mass m is only the force of gravity, F sub g, acceleration is due only to gravity, and we say F sub g equals ma. Hey, that's equal to mg. We express A as g when only gravitational force acts on an object. G denotes that acceleration is due to gravity. So it's common to label such force vectors as F sub g, W, or mg. We usually call F sub g, W, or mg the weight of the object. Later, we'll revise the definition of weight to include the force an object exerts against a supporting surface. When the net force on an object is its weight, Newton's second law tells us something remarkable: that whatever the mass of a falling object, acceleration is always g. Later, you'll learn about the gravitational field, the symbol of which is also g, the same g for acceleration due to gravity. The gravitational field surrounding a massive body is measured by the force per mass that acts on any neighboring body. That's g equals F over m, not surprisingly with units newtons per kilogram. Let me leave you with a question. Anyone who watches an apple and a leaf falling from the branch of an apple tree notices that the lighter leaf takes a longer time to reach the ground. So my question is, if there were no air resistance on the falling apple and leaf, and they begin their fall at the same time, which would reach the ground first? Until next time, good energy.